Welcome to ECE 320 homework set number 6. This homework set covered H bridges, DC to DC converters, and Fourier transforms. It is to analyze by hand a half H bridge. So the PNP, NPN on the left side, then the mirror making the letter H. This is half an H bridge. So I have 50 ohms going to 2.5 volts, just so I can see what's happening. For example, if I have, then the voltage I'm going to see is this one is 5 volts going to ground. That means this one's on. 0 volts across this diode. No voltage means no current. The NPN is turned off. The current then is 5 minus 0.7 over 1K, 4.3 milliamps. That turns on this transistor. I get a 0.2 volt drop across it when it saturates. 4.8 volts. 4.8 volts going to 2.5 volts at 50 ohms gives you 46 milliamps. And as a check, if I'm saturated, beta IB is more than IC. 100 times 4.3 is 430 milliamps. That's how much current I'm allowing to flow. I only need 46 milliamps, so yes, it is saturated. The resistor, the load, limits the current. This is 0.2. That's one case, current goes right. Second case, when I have 5 volts and 0 volts at the input. Here I've got no voltage across the PNP's diode, it turns off. I've got no voltage across the NPN diode, it turns off. Everybody's off, I just see 2.5 volts and no current. Third case, 5 volts, 5 volts. Again, I've got no voltage across the PNP, it turns off. I've got 5 volts across the NPN's diode, that turns on. The current then is 5 minus 0.7 over 1K, 4.3 milliamps. That allows 430 milliamps to flow. I'm only trying to push 2.3 volts over 50 ohms, 46 milliamps. So beta IB is more than IC. This saturates, and I'm at 0.2 volts. And that's the three cases. This is the reason I use 2.5 volts. In the lab, I can sit there and measure. If I'm 4.8 volts, I'm pulled high. 2.5 volts, everybody's turned off. 0.2 volts, pulled low. So I actually have 3 different voltages I can get out. Now in simulation, I can now check the answers using Circuit Lab. In Circuit, I'll build the circuit. Instead of using a 2.5 volt source at 100 ohms over here, what I'm going to use is just 200 ohms going from power to ground. The Thevenin equivalent is 2.5 volts, and the Thevenin resistance is 50 ohms. So that's the same circuit that I analyzed before. This is just a way to build it in hardware. Plus I'm going to add a 100 milliohm resistor. That just lets me measure the current. It's something close to 0, but not quite. You can actually buy 0.1 ohm resistors. This is the reason that they sell them. If I want to measure current, I'll just stick a 0.1 ohm resistor in series and then measure the voltage drop. Voltage is easy to measure, current is hard, so that lets me basically measure current. But anyway, suppose I've got 0 volts coming in. That says the voltage is at 4.84 volts. Easier to write than to say. Okay, so that means that the PNP up here is saturated. When it's saturated, we assume the voltage drop is 0.2. 0.2 is kind of an arbitrary number. It's close to 0, but not quite 0. This says the voltage drop is actually 0.156 volts. Yeah, close to 0.2. It is saturated. And this one's off. So that matches up. Second case. When I have 5 volts and 0 volts, this one turns off, that one turns off, and what I measure is 2.5 volts. That's the reason I've got these two resistors over here, so that when everybody's off, I have something to measure. I'll just measure the voltage across the voltage divider. The third case is when I have 5 volts and 5 volts. The PNP is turned off, there's no voltage across that diode. NPN is turned on, and I get 0.2 volts. So this is actually 0.086. Again, close to 0, not quite 0. We assume 0.2. This is actually better than what we assumed, closer to 0. In addition, I can see the current through the load. That's the 100 milliohm resistor. In this case, the current through the 100 milliohm resistor was plus 46 milliamps, minus 519 femtoamps, basically 0, and minus 48 milliamps, means minus 48 going right, plus 48 going left. So that matches up with our calculations. Problem 3 is build the circuit and take measurements. So here's my circuit, that's my H bridge. I can take the two leads, tie one to ground, tie one to 5 volts. So in these leads over here, the top one is 5 volts, the bottom one is ground. I can take these wires and move them back and forth and do the different cases. When I measure it, I'm expecting 0.2 volts. When I turn on the NPN, I simulated got 0.086. I measured 0.09. When their PNP is turned on, I'm expecting 4.5 minus 0.2. It's actually 4.884. Measured 4.96. Again, the voltage across the transistor is close to 0, but not quite. And when everybody's turned off, I expect 2.5. Close to 2.5. And the currents you can calculate. Here I calculated it. I know the voltages, I know the resistances, I can calculate the currents. Currents are hard to measure in lab. And typically that's what you do with currents. You measure voltages and then calculate currents. So that's problem 1, 2, 3. And here's the voltage. This is when the NPN is turned on, the voltage when the PNP is turned on, being pulled high. Okay, problem 4 is a DC to DC converter. Here I've got 20 volts powering the circuit. If I leave the switch closed, I'm going to power up V1 to 20 volts, and V2 will be close to 20, a little bit less due to voltage division. When the switch is going to discharge down to 0. As I chatter the switch, I can vary the voltage of V2 to be anything between 0 and 20-ish volts. Suppose I turn off the switch at 55%. So the voltage of V1 looks like this. It's 55% on. It's 20 volts when the switch is closed. It's minus 0.7 when the switch is open. If I do that, I have a DC voltage, an average. The average will be 55% of the time I'm at 20 volts, 45% of the time I'm at minus 0.7, for an average of 10.685 volts. Once I know the DC voltage of V1, I can find the DC voltage of V2. That's just voltage division. Inductors don't matter DC, capacitors don't matter DC. It's just 75 over 85 times 10, 9.24 volts. So that's the DC circuit. AC analysis. V1 looks like this. That's a challenge. I know how to analyze circuits when I have sinusoidal inputs. This isn't a sine wave. So I'm going to do a typical engineering solution. I'm going to change the problem, but change the problem in a way that it keeps the flavor of the old problem. This is a 1 kilohertz square wave. The peak-to-peak amplitude is 20.7 volts peak-to-peak. Let's pretend that V1 is a sine wave of 1 kilohertz, 20.7 volts peak-to-peak. Again, it's a slightly different problem, but it keeps the flavor of the old problem. And now I can solve it. If the answers are slightly wrong, I'm not too surprised because I solved a different problem, but it should be close. So going with it, at 1 kilohertz, the inductor becomes j omega L, J3 14 ohms. Capacitor becomes 1 over j omega C, minus J26 ohms. Put these in parallel, I get 8.3 minus J23 ohms. Now do voltage division. What I'm measuring over the total resistance times the input. So it's what I'm measuring over the total resistance times the input gives me V2. And note, this will be a complex number. I just take the amplitude, so take the phase shift and ignore it. What the phase shift tells you is that V2 is out of phase from V1. I don't care. I just want to know how big the ripple is. So that's why I took the magnitude. So that's what I predict. I predict the V2 will be 9.428 volts DC with a 1.78 volt peak-to-peak ripple. And again, you got to measure, got to put down the units on AC. DC is just a number. AC, I've got 3 units. I've got peak-to-peak, peak, and RMS. They're all different, so you got to label your answers. We're doing peak-to-peak voltage. In Circuit Lab, I can check my answer. Maybe, here we go. In Circuit Lab, this is how you build it. I'm going to use a pulse width modulation coming in. This goes from 0 to 10 volts. So for 55% duty cycle, feed it 5.5 volts in, I get a 55% duty cycle square wave out. That drives an NPN transistor as a switch. When this is 5 volts, the NPN is on, saturates. That allows this current to flow. That turns on Q1. That's your switch closed. When I have 0 volts at the output, that turns off the NPN, which turns off Q1, switch open. So there's my duty cycle. That's actually how you build it in practice. And this would be a microprocessor outputting a square wave. The duty cycle I can control in software. You could also use a 5 timer. That then drives my buck converter over here. If I measure the voltage at V1 and V2, here's what they look like. So not surprisingly, the voltage at V1 goes from minus 0.7 volts. Where that comes from is when the switch is open, I've got current flow. The current has to come from the diode, and the diode drops about 0.7 volts, making this minus 0.7. So that's down here. When the switch is closed, I get 20 volts out. It's actually a little bit less than 20 volts because I've got a transistor up here. I've got a slight voltage drop, ECE. This one's actually saturated. So I expect about a 0.2 volt drop. This should be about 19.8 volts, which is what you're seeing right here. There's a slight voltage drop across the transistor. Depends upon the current, but it's about 0.2 ballpark. That's V1. And here's V2. And notice it has a DC term and an AC term. The AC term is this guy right here. That's the voltage peak to peak, or AC voltage. The average is the DC voltage. That's supposed to be going down the middle. DC voltage. To find those, what I can do, there we are. I can take the maximum and minimum. The average is the DC voltage. The difference is the AC voltage in units of peak to peak. So comparing them, the DC voltage is fairly close, a little bit lower. The reason it's a little bit lower is because I didn't take into account the 0.2 volt drop across the transistor in the analysis. The AC voltage is a little high. We'll see the reason why when we get to problem number 7. The reason it's high, well, I changed the problem. Instead of a square wave in, I assumed it's a sine wave in. That's a little bit wrong, but close. In my book, if you want to get closer, throw it in Circuit Lab. Problem 6 is change the circuit so that the voltage at V2 is 5 volts and the ripple is 1 volt peak to peak. To set the voltage to 5 volts, what I need to do is change the voltage at V1. Let's go up a bit. So if this is 5 volts DC, I've got a voltage divider. V1 has to be a little bit higher than 5 volts so that by voltage division, V2 is 5. So if V2 is 5 volts, I need V1 to be 5.667 volts. The duty cycle, here just to be a little more accurate, I'm going to assume I'm going to go from 5.667 volts out. The input is 19.8 volts when turned on. The reason I did that is because you lose about 0.2 volts across the PNP transistor. Just to keep my answers a little more accurate. Plus 0.7, that's due to the diode. That gives you the duty cycle. A 31.1% duty cycle should result in 5 volts out, DC. To bring the ripple down to 1 volt, there's a couple ways to do it. Here, I'm going to use the previous answer. A 6 microfarad capacitor produced a 2.1 volt peak-to-peak ripple. To make the ripple 2.1 times smaller, make the capacitor 2.1 times bigger. One way to do it, there's other ways, but that's what I'll try. Throwing it in CircuitLab, you take the previous solution, which was this guy, change that to 3.11 volts, gives you 31.1% duty cycle. Change this to 13.3 microfarads and rerun the simulation. And that's what you get for V2. I can take the peak voltage, the minimum voltage. The average of the two is your DC voltage. I designed for 5 volts, and I got pretty close to 5. I designed for 1 volt peak-to-peak ripple, and I got 0.877. A little bit off. But that's design. Now, problem 8 and 9 looks at why is the answer wrong for V2. It's close, but slightly wrong. Well, the reason being is that we changed the problem. The input at V1 actually looks like this. It's a 1 kilohertz square wave, 55% duty cycle. From Fourier Transform says I can decompose this into harmonics. There's a first harmonic. Well, there's the DC term. There's a first harmonic. There's a second harmonic, third harmonic, and so on. Add them all together, I get the square wave. The nice thing about sine waves, once I do the Fourier transform, is I can analyze sine waves. I know how to do that. That's phasor analysis. So what I'm going to do is take this problem and use Fourier transforms, something you're going to cover in 343 Signals and Systems, and find the spectral content of it. Then analyze each circuit with a separate input using superposition to find the output. So first off, find the Fourier transform of V1. First step is to input V1 into MATLAB. I just said let's go from 0 to 1 second, steps with 10,000 points. I'm 19.8 volts, 55% of the time, minus 0.7 volts for the remainder of the time. And again, you could use 20 if you wanted. I used 19.8 just to make the answers match up with CircuitLab a little bit closer. The DC term is the average. The first harmonic, here I'm using the complex Fourier transform. My period is 1, so the fundamental frequency is 2 pi radians per second times 1. Here's the cosine term, sine term. Second harmonic, 2 times 2 pi gives you 4 pi. Cosine term, sine term. Third harmonic, 3 times 2 pi is 6 pi. Cosine term, sine term. So this would be the Fourier transform of V1. I've got a DC term, first harmonic, second harmonic, third harmonic, and the first harmonic is 1 kilohertz. Now if I plot V1, and here I actually plotted it out to 20 harmonics, this is what the Fourier approximation looks like. The red line, the blue line is the actual signal. As you add more and more terms, it gets closer and closer. So now let's analyze. At DC, here's my input. Here's the gain of the circuit. It's just a voltage divider. Output is gain times input. Output is 9.32 volts. First harmonic. Here's the frequency. Here's the inductor, capacitor, the capacitor in parallel with the resistor. See, the voltage division gives you the output at 1 kilohertz. Third harmonic, or second harmonic, the input at 2 kilohertz, the frequency, inductance, resistance, voltage division gives you Y2 at 2 kilohertz. Third harmonic, here's the input at 3 kilohertz, the frequency, resistance, inductance, voltage division, output at 3 kilohertz. So here's the answer. That's actually what CircuitLab is giving you, except it's giving you to more terms. In theory, you have to go out to infinity. In practice, this third harmonic is so small, if I ignore it, I'm not too far off. In fact, the second harmonic is pretty small. If I just included the DC term and the first harmonic, I'd get a much better answer. And this is the reason, or how to get an answer that's more accurate. Instead of saying that the input is a 20.7 volt peak-to-peak sine wave, what I really should do is find the first term in the Fourier transform. Oops, other way around. I should find the first term in the Fourier transform for x1. And if I were to use this as my AC input, 25 volts peak to peak instead of 20.7, I'd get a more accurate answer. But that's, again, from the Fourier transform, it's a lot more work for slightly more accurate answers. But you can do it if you want to get the more accurate answers. So that's kind of why you cover Fourier transforms when you get to signals and systems. For the rest of this class, we'll just assume this is 20.7 volts peak to peak. Call that the AC voltage coming in. A little bit wrong, but close. If you want to get closer, throw it in Circuit Lab. So that's homework set number 6 for ECE 320.